Okay, so maybe I will first give a little bit of information about Zalando, because when I got hired by the company, I did not know what it was, and I was working in the States, so I'm also paid, at least partly for the trip, by employer branding, so I feel somehow compelled to do this. So it's, according to our PR department at least, we are the leading online fashion platform in Europe. We're operating in 15 mostly Western European countries, 11,000 employees, and we have at any time 150,000 items in store, 19 million active customers, 1,300 employees at technology at Zalando in Berlin, mostly, and about 75 data scientists and growing. And I put this in color because if you think Berlin might be the place for you, so you can check out these web pages. Okay, so since we're an online company, we have lots and lots of data. So we have information for about 1 million different articles that we have in store or had at some point in store. Some 100 million sales events. So this is only things that customers actually bought and kept or forgot to return. And we have about 40 million customers in Europe, which is kind of crazy because there aren't all that many people in Europe. So 300 million, yeah. So we have all this data, but we didn't make good use of it, we think, because we have sales data and kind of in a parallel universe, we had content data. Obviously, if you want to sell things online, you have to put a web page on there, and this is based on images, on brand, and this kind of information. And we really want to integrate that a little bit, and in that way, we should obviously get a little bit better view of what customers, individual customers actually want. We also would like to get a better view of what we actually have in store. Just imagine 150,000 things. Who can keep this stuff in the head? So we want to map out the articles, what are the relationships. And fashion DNA is obviously just a buzzword that some higher up in the company likes, so I should explain a little bit what that is. Yeah. So let's take this little example that we have here on the left. There is an article that we actually are selling currently. So if you're interested, yeah, just go to the catalog. We describe a shirt like that by a particular fashion DNA vector. So it's a bunch of numbers basically that describes that article. On the other hand, we have lots and lots of customers. Let's say we have a model customer that, let's call him Jeff maybe, yeah. I would like to describe their taste somehow, so they have some sort of personal style, and I will call this style also by a vector, the customer style vector. You could say it's their style DNA, but it sounds so stupid that I probably better let it be. And all that we want to insist on at that stage is that they have the same dimensionality. It's the same set of numbers in dimension. Let's assume that something like that exists, then we can say we can compare articles. So if you look at the left, I have 2 T-shirts. We're keeping with this kind of space theme, I guess, this time around. Are they similar? Are they dissimilar? To what degree are they similar? Well, we can compare the fashion DNA vectors for them. The more they are aligned, the more similar we would consider them. And similarly, we can also take 2 customers, like the 2 on the right-hand side, and ask ourselves how similar are those in style, more or less similar. And again, we can do this by comparing basically the direction of these vectors. And then, of course, most importantly, we want to know whether a particular customer likes a particular item or dislikes it. And that we do by comparing basically the vectors for the article and the vector for the customer, so we get some sort of affinity. They might be more or less aligned, more or less inclined to buy such an item. Ideally, we should take this affinity that we have defined before and somehow translate that in the probability that that customer actually will buy that item. After all, the whole company lives from that. Yeah, so we should try and get as accurately as possible a forecast whether customer Jeff likes Star Wars t-shirts. And the way we do that is basically we take this affinity and transform it into something that looks like a probability from 0 to 1. And what we want to do is basically train an algorithm that now delivers vectors, fashion DNA vectors, style vectors, that come in the probability as close as possible to the actual ground truth. And the ground truth is what has happened before. We have this huge matrix of customers and items. Some items were bought by some customers, mostly nothing happened. And we want to make sure that the probability that we forecast is as closely related to what actually happened as possible. And we do this using a logistic loss here. This is not entirely new, of course. Other people have done that before for Netflix and so on and so forth. So what you've seen so far is just in quotes, a logistic matrix factorization model. And our claim is that this is not really good enough for fashion. Maybe it works with movies and music, but with fashion we have a lot of problems. And one of the important problems, and this also came up in the talk before, is that you have this very rapid turnover in the fashion industry. So we have a season twice a year. Within a season, about 150,000 articles get exchanged in the catalog. And if you calculate that back, that's about 1,000 a day or 1 every 2 minutes. So basically, we have never the same catalog when I look. So there's always something new. And that and the fact that most customers never buy a given item makes a recommendation that's based on sales only very hard. The other thing is that so far we politely ignored the fact that we have actually information about the articles. We know what they look like, we know what brand they are, and so on and so forth, and we should definitely use that fact. And so the idea is to build something where we can already forecast some kind of interest among customers, even for articles that just enter the store. We want to recommend them to people immediately. And because we have 40 million customers, and it's very hard to train a model on 40 million customers, we want to create a model with just a subset of customers, and afterwards, if we have to do it for another customer, just very quickly produce their own style vector so we can use the algorithm. How does this work? Well, within the machine learning community, deep learning is kind of the fashionable thing to do, I could say here. So deep learning is basically just nonlinear transformation of features. So if we have features like image, here this Wonder Woman t-shirt, where we have, let's say, image information, we have tag information like the brand and what it is, and it's for females, and it costs $27.90 or something like that in our store. We somehow want to use this information to get a numerical description of that article, and this neural network will do that for us. So a convolutional network for image data, it's very common. A fully connected network for all kinds of discrete data that we have in here, like the brand. We put everything together and come up with a fashion DNA vector. In this case, we had a length of 256 for that, 256 numbers, but this is kind of a detail. And you see that basically once you know what it looks like, the article, we can calculate that fashion DNA if we know what that network looks like. And the idea is now that we train what's in the network using the sales. So we have on the left-hand side exactly what you saw before. We have the data that is in the catalog, the neural network that transforms them. And now we calculate probabilities out of that fashion DNA together with the data that we have for 27,000 frequent customers in our store. We compare what we get out from the model with the actual purchases of those 27,000 customers, and we use the comparison to train our model. So by backpropagation, we change how the network works. We also change what the customer styles look like. And we do that until it doesn't get any better, and that is the model that we get then. Once we have trained this model, now it's easy for us to produce a fashion DNA vector for new articles. So for example, even if nobody has seen the article before except us, we can put in the information, just push it through. We get fashion DNA, and for our customers, that we used for training, we can immediately calculate the likelihood of purchase from that. It's a forecast, so we can do recommendations with that. Wrong way, sorry. If we have a candidate that we didn't use for training, we can basically do the same thing, just we keep to the right. We can look what they have bought in the past. We keep the fashion DNA fixed. We look at the purchase probabilities. We use logistic regression in order to calculate a style vector that comes closest to the former purchases. And in that way, we can very quickly assign styles to such customers too. Okay, evaluating recommendations. We want to know how well this works, obviously. So in this case, we have to be a little bit careful because now we have actually 2 trainings and test sets in here. We have a training set of articles. So we split our 1.3 million articles into 90% training and 10% just for testing. In real life, this would be the new articles that we put in here. And we used 30,000 customers, and we kept 3,000 out of the loop just for testing purposes. And what we're really interested in is how well does this thing work for such articles that had not been used in training, for such customers that had not been used in training, and that's the orange square up out there. So this is the real test for a system like this. One thing that we did is we calculated a lot of purchase probabilities in here. So we used 200 million pairs of customers and items out of the holdout sets, sorted them out and put them into 200 bins. So every red dot on the graph represents 1 million customer article pairs. On the very right, you will see some that were very likely ending in a purchase. On the very left, things that apparently did not match the customer at all. So we have very low probabilities. And we compared that to how many purchases actually happen in these bins. If we were strictly on the blue line, we would have a perfect match. And you can see for the articles that are likely to be bought, we almost get that. So we get a very good agreement between predicted purchase likelihood and the actual purchases that happened. How well does it work? I will keep this short. So there's measures for recommendation to quantify recommendations. Here I use receiver operating characteristics. We can talk about this later on in detail. The higher the number that we have on the right is to 1, the better the recommendation will be. 1 would be the perfect recommendation. So a curve that is high up and a high number is good. We see that we get fairly high numbers in here. And in particular, we don't get much of a drop if we go from the things that we have seen in training, that would be the blue square, to things that are completely out in the test set, the orange square. And because things are nicer with pictures in fashion, here we just picked a random holdout customer. So that's probably a woman, because most of our customers are women, as a matter of fact. Yeah. What is shown on top, these are the articles out of that holdout set that the system didn't see in training that the customer had bought. And you see it's lots of pinkish stuff, lots of green stuff, lots of striped stuff. And then we asked our recommender what it would recommend, and the top recommendations among these 130,000 articles that are in the test set, they are in the middle line that you can see here. And if you look very carefully, you will see that actually, first of all, it looks a little bit like what the customer really bought, and there's an actual match in there, so I leave it up to you to find that one. Yeah. At the bottom line, I plotted up what the algorithm thinks are the least likely purchases, and you see you get male stuff, you get kid stuff. So apparently this customer is not very interested, at least in shopping for these customer groups. Yeah. You also see that, for example, plaid, unlike stripes, doesn't seem to really hit it with this customer. Okay, 2 more slides that I will have, and then I will be done. So this was the recommendation part, matching customers and articles. Now for the mapping part, where we're just comparing article to article. What I did here is I picked by chance some articles within the catalog, and I plotted out the articles that are closest by in our fashion space. On the top we have this maternity dress, At the bottom, we have the bow tie. These are rather unusual items in our catalog. It's not like t-shirts. Yeah. Just wanted to show a couple of things with it. On the top, you see that you get, of course, more pregnancy dresses that are similar, considered similar. But you also get some maternity tights. And most interestingly, you get a baby outfit in there. So the system, after being trained on sales, knows that maternity something has to have to do with kids. Yeah. That's nowhere in the data that we fed in, except for the sales. On the bottom, you see that a bow tie is considered similar to a regular tie. If you're interested what can happen if you leave out part of the information, we can talk about this later on. I have some interesting things for that too. And then the last serious one that I have in here, you can use a lot of items and try to map them out. This is called a TSNE map. Those are very popular to kind of project them down on a few dimensions. And these are 3,000 articles that are somewhat popular, now ordered out on that map. The interesting thing is that you see that's a complete hierarchy that you get in here. So there are 3 big worlds out there. The biggest world of all is women's fashion. This is not very surprising if you ever worked in a fashion store. But there's a separate world of male and another one that has kids, babies, and maternity in it. And in each of them, you get, again, subdivisions. For example, if you look at the bottom left, you will see that in the big women's section F, there is a shoe section. All the shoes are showing up there in G. And within the shoes, you might have, for example, high heels that would be in L. By the way, across from L in M, that's evening dresses, so this somehow goes together with high heels, apparently. And I have this as a map. I will put it onto the wall so you can study that in a little bit more detail later on. Right now, it just looks like flies, of course. Yeah. Summary, we try and put together a model that has content and sales together. We use deep learning and matrix factorization. We can solve the cold start problem to some extent. We can generalize on more customers, and the purchase probabilities that we get are pretty good. If we map out articles, we find that the mapping makes sense. And with that, I would like to thank these 2 people. They are my colleagues at Zalando in Berlin, Sebastian Heinz and Roland Vollgraf. And of course, I would also like to thank you. Thank you very much. And maybe there's time for questions. Yeah.